So for our next part of this sound unit, we're going to begin talking about the Doppler effect. And the fancy scientific definition of the Doppler effect is the apparent shift in frequency caused by the relative motion between the source and the observer, which probably means very little to you. The other way of saying it is basically that ambulance sirens sound different when they're going towards you versus away from you. And that really is what the Doppler effect is all about, is that change in the frequency, the change in the pitch of a sound when the sound is moving towards you versus away from you. So I think the best way to really understand this, and it's absolutely something that all of you have experience with, is to hear it, right? The best way to understand the Doppler effect is to hear it. So we're going to look at two quick examples of the Doppler effect occurring. So our first one is going to just be with a car horn, and while you can see the video here, you don't even really need to see it. The key is the audio piece. You'll be able to tell me exactly what's happening in the video just based off of the sound you hear. So that sound there, that shift, that is the sound of the car going past. And that right there is a perfect example of the Doppler shift, okay? The frequency you hear when it's going towards you versus away from you changes. You have a higher pitch, higher frequency when it's going towards you, and a lower pitch, lower frequency when it's going away from you. One last example here, this one's maybe slightly more annoying, but I promise this is the last annoying sound of the video, is with a European fire truck, which has a very interesting fire siren sound, but it really exemplifies that Doppler shift here. So here comes the fire truck. Right there, you really hear that shift as it goes from the higher pitch, the higher two tones, to the lower two tones. And that, once again, is that Doppler shift. The motion towards or away results in a change in the frequency, which is a change in the pitch. So why exactly does the Doppler effect occur? It's all about what happens with the sound wave. So when we're thinking about this fire truck here, and this fire truck is moving towards this person, and this example we have the source of the sound moving, but it doesn't necessarily have to be the source of the sound. It could be the observer moving, but we'll just talk about the source of the sound moving for now. So we have this fire truck moving towards the person, and it is outputting these sound waves. But what ends up happening is as it outputs these sound waves, okay, it's moving towards those sound waves. So it's almost like chasing the sound waves that it just emitted. And so that ultimately ends up resulting in a situation where these sound waves get bunched together, okay, smushed together. The reverse happens when it's moving away, because it emits the sound wave going back to the left here towards the person, but the truck itself is moving towards the right. And so what we end up seeing is those sound waves get spread apart, because each time it emits one, it goes away from it, and so it increases the gap. So we can clearly see here the distance between the sound waves is much smaller than it is here. It's a smaller wavelength. That smaller wavelength results in a higher frequency, whereas here we have a bigger wavelength, which results in a lower frequency. Okay, and we see the exact same thing, maybe a little bit more extreme here with the police car, but same basic idea. The person over here, where the car is moving towards them, we'll see these waves bunch very close together and hear a higher frequency. The person over here, when the car is moving away, will see the waves much further spread out and see a lower frequency. Mathematically, this is the equation we have for the Doppler effect. So we can calculate this shift in frequency based off of the motion of both the source, the person or the thing creating the wave, and the observer, the person or the thing hearing the wave. And so what we have here are the two different frequencies, f sub o and f sub s, which are the frequency of the observer. Okay, that's the frequency that's actually heard, and f sub s is the frequency of the source, the frequency that's emitted. All right, and then we have this fairly tricky fraction here, v plus or minus vo over v minus or plus vs. And these v's here are a constant. That is the speed of sound in air, which for our purposes we're always using as 343 meters per second. We have talked about how that changes some with changes in the medium, but we're just going to go with, to simplify it, 343 meters per second. And so that's that V always, that doesn't change, that's a constant. And then these two V's, V sub O and V sub S, represent the velocity of the source and the velocity of the observer. Okay, so motion of either thing, either the source or the observer, will result in this shift. And those V's represent how quickly those things are moving. We'll talk about the plus minus bit in a second on the next slide. So as you may have noticed, this equation, and this is really probably the first time we've had this all year, we have this plus or minus symbol on both the top and bottom of that fraction. So a really important question is, how exactly do we decide whether it's minus or whether it's plus? What I always do is I always keep in mind two very important concepts related to the Doppler effect, and that is that whenever the objects are moving towards each other, the frequency will increase, okay? And whenever the objects are moving away from each other, the frequency will decrease. And based off of that, you can just kind of reason your way through, should you add or subtract on the top, should you add or subtract on the bottom. So knowing that the frequency of the observer must be higher, we want this number to be as big as possible to increase the frequency of the observer, because we're multiplying it by the frequency of the source. So how do we make that frequency increase? Well, on the top of the fraction we want a bigger number, so we're going to add. On the bottom of the fraction, because we're dividing, we actually want a smaller number, so we're going to subtract, right? We'll end up with a greater frequency if we multiply by a bigger number on top or divide by a smaller number on the bottom. And the flip is true when we're moving away. All right, when we're moving away, we want to decrease the frequency. So we either want a smaller number on top, which is why we subtract, or we want to divide by a larger number on the bottom, which is why we add. So what I would say is you can either kind of remember that idea, this fundamental idea that motion towards increases the frequency, motion away decreases it, and just base your plus or minuses off of that. And you always can go ahead and calculate it, and if you get something that contradicts this, you know that you picked the wrong sign. Or you can just kind of use this here as a little reference whenever you're doing these problems. All right, for this next one, we are looking at a situation where a person is marching and playing an instrument. So here is our person. They are moving towards you and they are playing some musical notes here with some instrument. I'm never going to attempt to draw that. And then you are over here listening to the sound waves being emitted from this person's instrument. And we want to know, how does their motion affect the pitch, which, keep in mind, pitch is frequency when it comes to sound waves, and how does the motion affect the volume, which is the amplitude. So to answer that first question, the pitch is affected. That's the whole idea of the Doppler effect. And the motion towards means that the frequency is increased. And so their motion will increase the pitch. So technically, when someone is playing in a marching band, if they are marching towards you playing a musical instrument, the pitch that they are actually playing and the pitch that you hear are not going to be the same. So you might actually hear a pitch that's slightly higher than it's supposed to be. Now, obviously a person marching is not going to be moving that fast, so it's really not going to be that dramatic of a shift. I have no musical ear whatsoever, so I definitely don't notice a difference, but maybe some people who do have a better musical ear will notice that pitch is slightly off. However, it does increase the pitch a little bit because the frequency goes up. Amplitude, on the other hand, is not affected by that motion. The Doppler effect is solely about the frequency, so there is no change to the volume when they're moving towards you, other than the fact that being in close proximity obviously means it's louder, but that motion by itself does not actually change the volume. It just will get louder because they are closer to you than when they were further away. All right, so let's go ahead and do an actual math practice problem here using this Doppler effect equation that we just introduced. So for this particular problem, we have a prison siren that is emitting a sound and a prisoner running away from the prison siren hears a different pitch because of their motion. So we're told that the person running away, the prisoner, hears this frequency. So that is the frequency that's actually heard. That's going to be the frequency observed. But the actual frequency of the siren, the prison is emitting, is this 440 hertz here. And so that's going to be the frequency of the source, okay, which is F sub S. So let's go ahead and fill in those things that we know. We'll fill in a few other things we know and go from there. So the frequency observed is this 400. That's equal to the frequency of the source, which is 440, times, and then we have this big fraction here. So V plus or minus VO and V plus or minus VS. We know that V is always 343 meters per second. That is the speed of sound in air. So we can fill that in for V on both the top and the bottom. It doesn't cancel out though, because we also have this plus or minus VO or VS piece. Now, the velocity of the observer, that's what we're looking for. So I'm going to leave that as VO because we want to know how fast the prisoner is running. The prisoner is the observer. And then we also need the velocity of the source, but in this case, the source is the prison itself. All right, and so we can say the velocity of the source is 0 because the prison itself is not moving. Now we need to figure out our signs, and I always save this for last. And so what I always do is I always think again about that logical piece. What do I know should happen to this frequency? And we actually can see that the frequency observed is lower. And the reason is motion away leads to a decrease in the frequency. Okay, so we can say if we want to decrease the frequency, what we want is we want a smaller number on the top and a bigger number on the bottom. So for this smaller number on the top, I'm going to put a minus. On the bottom, we want a bigger number, so we would add, but it really doesn't matter here because it's 0, so really that sign is irrelevant. And so what we end up getting here is 400 equals 440 times 343 minus VO all over 343. Okay. From there, we can go ahead and solve for that VO. So the first thing I'm going to do is I'm going to divide both sides here by 440. And what I end up getting here is 0.91 is going to be equal to 343 minus VO all over 343. I'm going to multiply both sides by 343. And when I do that, I end up getting 311.8 is going to be equal to 343 minus VO. I'm going to subtract 343, and I come over here and get negative 31.2 equals negative VO. Since they're both negative, I can just multiply both sides by -1, making them both positive, and I get that the velocity of the observer is 31.2 meters per second. This is a very unrealistic number, but in order to really get a significant Doppler shift like we see here, the objects have to be moving relatively fast. That's why a person running, you probably really wouldn't notice too much of a Doppler shift. So we made the problem a little bit unrealistic just to get a bigger Doppler shift here. All right, so let's do one more practice problem here. So in this case, we have a car that's driving down the street here at a speed of 12 meters per second. That's my terribly drawn car there. So going at 12 meters per second towards a runner that's going in the opposite direction here at 4 meters per second. And the car is going to go ahead and hit its horn, creating that sound. And the horn itself has a frequency of 300 hertz. So let's think about what numbers we have here. So this 12, that's going to end up being the velocity of our source here. The 4 is the velocity of the observer. The runner is the one hearing this sound. And so that's going to be the velocity of the observer. And then lastly, we have this 300 hertz. and that's going to represent the frequency emitted by the source, so f sub s. So let's go ahead and fill in what we know here. We're looking for the frequency heard by the runner, which is that frequency observed. That's going to be equal to the frequency of the source, which we're told is 300. And then we're going to set up that fraction. So we have 343 on both the top and the bottom for the speed of sound in air. And then we can fill in the velocity of the observer and the velocity of the source. So the observer is going at 4 meters per second. The source is going at 12 meters per second. Here's where we got to do our sign check and figure out if we want to add or subtract. And what we are going to keep in mind here is that motion towards results in an increase in our frequency. Okay, and so what we want to do is we want to have a bigger number on top, so we're going to add, and a smaller number to divide by on the bottom. And yes, you will have times where both objects are moving, and that's perfectly okay. You're just going to kind of think about what that motion is and how you want the top to act, how you want the bottom to act, so that you ultimately, in this case, get a bigger number. And so we have the frequency observed is going to be equal to 300 times 347 divided by 331. And when we go ahead and solve that problem for the frequency observed by the runner, we end up finding that the runner will observe a frequency of 314.5 hertz, even though the source is emitting a frequency of 300 hertz.